Right. It's time, and I'm switching to English now. And I'm not sure that I did it right. So I have to start with sharing, I guess. And now to start. So topic of today's lecture is molar activity. And this is one of the basic notions in radiopharmaceutical chemistry. And there are still controversy about this issue. So it was so much controversial that during latest session of European Association of Nuclear Medicine, there was a big session concerning molar activity, and I was asked to give a talk among 3 other speakers. So I will continue. And I will start with definition, because earlier when I started to work, there was a parameter called specific activity, which has been defined as activity per unit mass of the probe. People use it in different ways. Some say that, wrote that about activity per microgram. Some wrote about activity per micromole. And it was not a big deal when the majority of PET tracers were small molecules. However, during at least 20 latest years, there were introduction of large imaging probe like antibodies with molecular weight of 150 kilodaltons as opposite to 300 daltons. So the microgram were not informative. So relatively recently, now 3 years ago, there was an editorial in Journal of Nuclear Medicine and Biology, and there was a suggestion to distinguish strongly specific activity as activity per unit mass of imaging probe expressed in microgram, or molar activity, which is activity per unit of amount of imaging probe in micromoles. And we will continue to use this terminology with molar activity. The history of question would be better elucidated if we would just consider how small amount of substance we have to handle when preparing radiopharmaceuticals. For example, typical injected activity of technetium-based radiopharmaceuticals is 370 megabecquerel, 10 millicurie. It's relatively easy to calculate how much is it in grams or micrograms. So we do know that by definition activity is equal to lambda n constant, decay constant multiply by number of atoms. So we know the ratio between decay constant, which is a logarithm 2 divided by half-life, and if we know activity and we know half-life of the radionuclide, we could define how many atoms are there. So 10 millicurie or 370 megabecquerel of technetium-99 is approximately 10 to 12 atoms. Well, it sounds a lot, but if we convert this amount in moles, so using Avogadro number, we could relatively easily find that we are talking 10 to minus 12 moles. So we handling picomolar amount of the substance, or it would be roughly 20 nanograms. Is it easy to handle this amount? I can tell you not. So what does this mean? It's extremely low amount, extremely low concentration. Even if you use the purest solvents or buffers, any impurity would be in huge excess in comparison with your radionuclide, which can modify its behavior. Moreover, we're working with ionizing radiation. There happens radiolysis of water or working solution, and when your nuclide is presented in such a small amount, it could be relatively easily oxidized, for example. So that is the trouble. So to handle this situation, in early days, radiochemists start to work with so-called carrier, which is defined that as inactive material deliberately added to specified radioactive substance to ensure that the radioactivity will behave normally in all subsequent chemical and physical processes. Well, when Curie started to work with uranium, plutonium, the only established separation technique was precipitation. And if you handle nanomolar amount, you might be well below solubility product, so you don't have a proper precipitation. So one could use those macro components to make your work more handleable. It might be isotopic carrier when you add stable isotope of the same element as a radionuclide. In some cases, it works with so-called non-isotopic carrier when you using chemical analog and let your substance behave in this way. For example, one could use rhenium as non-isotopic carrier for technetium. So it simplifies life for radiochemists. And a lot of interesting and important work has been done using carrier-added nuclides. Moreover, very often the nuclides which have been used by researchers were carrier-added a priori. The most common way to produce nuclide was neutron irradiation in nuclear reactor. In this case, a typical reaction was N-gamma, so the target element caught or captured the neutron and de-excited by emission of gamma rays, and the mass number was changed, but at the same time, Z or charge of nucleus was not changed. So we induced activity, but we did not produce atom of other elements. So separate isotope of the same element is not trivial task, and apparently typically the target material followed the radionuclide as a carrier throughout whole processing. Still, it worked, and it worked properly. Before we started to work with molecular targeting, as long as you're using physiology or follow the blood flow, for example, or air, the specific activity doesn't matter. It started to be a problem when we came to molecular level. And the situation here is described by equation of binding of a ligand to receptor. And we could apply, of course, the same mathematics to any kind of specific binding. So the binding of a ligand to receptor is described by equation that B, which means that bound ligand concentration is equal to Bmax, number or concentration of binding sites, multiplied by ratio of free ligand concentration over sum of Kd and free ligand concentration, where Kd is apparent dissociation constant at equilibrium. And one often express affinity as a Kd. Good radiopharmaceuticals have affinity or Kd in a low nanomolar or single digit nanomolar range, or even subnanomolar. So what happens in this case? So if F is very low, so the number of bound substance would be equal B max over Kd, because we could neglect concentration of free ligand. And this is called, sorry, it's would be equal to 0 because F would be equal to 0. So when the concentration of free ligand will grow, the binding will start. At a concentration of free ligand equal to Kd, it would be approximately half of maximum bound amount. And when you reaching approximately concentration equal to 10 dissociation constant at equilibrium, the binding will be saturated. So whatever you adding to your solution, there will be no binding more. No specific binding, I would say, because there is always in biological system sort of unspecific binding. And unspecific binding is typically directly proportional to concentration. So if you increasing the concentration of your ligand well beyond dissociation constant equilibrium, so the contribution of unspecific binding will grow, grow, and grow. And in the end, the specific and saturable binding will just be drowned in the non-specific binding. So predominant mode of binding will be unspecific. So the possibility to bind specifically is always limited. And that might create a problem. For example, this is example from our work when we try to develop targeting of prostate cancer using bombazine analog, antagonistic bombazine analog. And what we could see that when we increase the injected amount of this radiolabeled peptide, the radioactivity bound to tumor was decreased. The same happened in activity in pancreas, and this was also through receptor-mediated binding, because pancreas expresses gastrin-releasing peptide receptor, which is a target for bombazine. So specific binding decreased with increasing amount of radioactivity. At the same time, activity in kidney did not decrease. So uptake in kidney was absolutely unspecific. So that remains to be at the same level. So we had a problem because we need to deliver certain amount of radioactivity. We could not have infinitely high specific activity, but when we increase the targeting agent mass, we have a decrease of specific uptake in tumor. So in this situation, when you need to perform radionuclide therapy, the molar activity, amount of injected protein must be low and molar activity must be high. You don't have any choice. Another example is imaging of so-called high affinity, low capacity system. And this is typically a situation with a majority of brain receptors, so the central nervous system receptors, where we have dopaminergic receptor and serotonin receptor and so on. So it didn't work for quite a long while, so you could synthesize a ligand, and in early days there was always a high amount of carrier called carbon in carbon 11 tracers, so there was no activity. Ben Klonström from Uppsala revised the whole procedure and identified the sources of cold carbon in preparation of carbon 11 labeled radiopharmaceuticals, and managed by several orders of magnitude increase specific activity, which means that to inject the same activity, you inject in much less mass. Here you could see the image of dopamine receptor in brain at high specific activity with a low injected mass. The receptors location was clearly visualized. If you decrease specific activity, well, you need to have a believing eye and good imagination to see places of binding of this ligand. And if specific activity was really low, you don't see any specific binding. So apparently, when you working with a high affinity, low capacity system, you need to have high molar activity. And low capacity means that you have a low concentration of your target in target volume. So generally speaking, that in the case of radionuclide therapy, molar activity must be high. I would dare to say as high as possible. In the case of imaging of high affinity, low capacity system, molar affinity must be as high as possible. And adding of a carrier is utterly undesirable in this case. So there was a realization, and there was sort of gold rush for high specific activity. So a number of researchers and a number of companies start to declare they produce a carrier-free radionuclide. So that means that it does not contain a single atom of stable isotope, which is unfortunately never truth. We always have sort of contamination with stable nuclides. And there are only a few exceptions. For example, artificial transuranium elements. They do not exist in the mother nature. So they could not be in preparation, so it might be truly carrier-free. One could discuss if you have a non-isotopic carrier, but it's generally speaking carrier-free. The same is, for example, therapeutic radionuclide astatine 211. There is no stable astatine in the nature. So there are several astatine isotopes which could be encountered in the decay chain of uranium and thorium, but total mass of astatine on the planet Earth at any moment is a few milligrams. So that also means that we could assume that astatine is carrier-free. In majority of other radionuclides, there is inevitably some amount carrier. So now there is a consensus definition. If you didn't add stable isotope deliberately to your preparation, you should call it no carrier added, but no carrier free. Or you must present evidences that there is no carrier. So, the many medical isotopes falls in this category. For example, cyclotron-produced radionuclides are typically no carrier added. The reason is that you use charged particles to induce desirable reaction. It typically results in the change of charge of the nucleus of new radionuclides, so it belongs to other elements, and chemical separation of different elements is not really a big deal. So you could always purify the radionuclide from target material. So there are no carrier added. There are some approaches to production of radionuclide using nuclear reactors which also produce no carrier added nuclide. Typically, when irradiation with a neutron of target material produces a radioactive daughter, which in turn decays to the desirable radionuclide. Well, good example is production of lutetium-177. So it might be produced directly using isotopically enriched lutetium-176. So N-gamma reaction. It's a very efficient reaction, but still you have majority of atoms belonging to stable isotope. But you can irradiate ytterbium-176 with neutrons, so that would produce ytterbium-177, which within a couple of hours would decay to lutetium. So now you have target material, which is ytterbium, but product is lutetium. Separation of lanthanoids is not really easy, but still it's possible. So this way, no carrier added lutetium could be produced. Unfortunately, especially commercial suppliers still using this label carrier-free, which is deceptive, because typically you have much more mass in your preparation than in carrier-free status. So we typically try to work with no carrier added radionuclide and with no carrier added label compounds in radiopharmaceuticals. Now we coming to more controversial area. So how we work, how we define injected radioactivity of radiopharmaceuticals. We need certain amount of radioactivity to be concentrated in target organs. The reconstruction the algorithm which enable us to reproduce activity distribution using, for example, monitor are dependent on activity. Strictly speaking, the higher is the activity, the easier and the more accurate you could reconstruct the activity distribution, and the more accurate image you will receive. On the other hand, we cannot inject infinite amount of activity in living patient. So the first stage, the first phase in development of any radiopharmaceutical is determination of the symmetry. And you could see how much absorbed dose would be delivered to every organ for any amount of injected activity. So then regulating authority or ethical committee define how much activity for every radiopharmaceutical you could inject, and not more than that. So we could say that for every radiopharmaceutical, the injected activity more or less fixed. It's maximum permissible. So when we talking about molar activity, it means that the only variable we have is amount of imaging probe, micromole. And in this situation, apparently that molar activity means for that high molar activity means low amount of injecting imaging probe for any given injected activity. And question is low injected amount always good? The question is that when I started my PhD study in 90s in Uppsala, the first paradigm, the first dogma we have to learn is that molar activity, at that time used the term specific activity, must be as high as possible. Taking into account that high specific activity ligands has been developed in Uppsala first and really made miracles, essentially created the molecular imaging. So that was very clear to me. I always have to strive for high specific activity. However, the first bell rang in 1994 when Rotterdam Group started to work with radio-labeled somatostatin analog, octreotide. They managed to image somatostatin receptor in neuroendocrine tumor and started to investigate what activity you have to inject to get the best image. Unfortunately, it has never been published as a full paper, but abstracts say that if you decrease injected mass, the quality of image would be much worse, and even the tumors might be missed. So this fact was mentioned in one abstract and in one review paper, no original paper, but later Marion de Jong published her work and in rat using somatostatin analog, and she demonstrated famous bell-shaped curve, which suggests that if you inject too little, accumulation of tumor would be very low. If you start to increase the mass, uptake in tumor is increasing, and then the blocking effect start to play a role and activity will be decreased. So that was a challenge of public opinion in this area. Nowadays, it's very clear that it's actually no-brainer. The dissociation constant of octreotide is 5 nanomole. So if you inject 1 microgram, it is exactly 1 nanomole. So extracellular volume of human body is roughly 14 liters. So in the end, you get approximately 0.06 nanomole concentration. It's much lower than dissociation constant. There couldn't be high binding. So, but this is the first sign that the high molar activity or low injected mass is not good. Later on, that has been confirmed in another model of neuroendocrine tumor in Gothenburg, Sweden. And again, one could see the bell-shaped curve in the dependence of tumor to non-tumor ratio at different masses. And the lowest mass, highest molar activity is providing low contrast. So that means that it is a bad idea. Later on, it has been also demonstrated for other types of targeting peptides, for example, for antagonistic analog of bombazine. It has shown by Schumacher and co-authors, where the highest tumor uptake, significantly higher tumor uptake, was obtained by injection of 15 picomole of bombazine per animal, while injection of smaller mass would result in lower uptake. Later on, we worked also with antagonistic analog of bombazine, and again, the highest injected specific activity or lowest mass resulted in lower uptake compared to optimal. The same effect has been observed for targeting of glucagon-like peptide receptor using exendin. Again, too low injected mass or too high specific activity resulted in lower tumor uptake compared to the optimal specific activity. So, the conclusion from those studies are that for several radiolabeled peptides, the lowest injected mass does not provide the highest tumor uptake and the highest tumor to organ ratio. So optimal injected mass is not the lowest one, and accordingly, the optimal molar activity is not the highest one, which was once upon a time nearly revolutionary rebellion conclusion. Optimization of injected mass might happen if we target so-called shed antigen. So several tumor-specific cell surface target might be dropped by tumor cell and enter circulation. That might be enzymatic cleavage of such protein, or just they drop it during the normal processing of cellular development. For example, of the carcinoembryonic antigen or tumor-associated glucoprotein 72, which are very popular pancarcinoma antigen in development of targeted pharmaceutics, are shed antigen. And constantly certain amount of this antigen present in free form in circulation, not only in tube. Several other antigen which have been discovered recently and considered as a druggable target in cancer cell are also shed, like methicillin or human kallikrein 2. So what happens? If this antigen exists in circulation and you inject radio-labeled antibody, so an antibody and antigen are ending up in the same compartment. It's easy for antibody to target, to shed antigen in the circulation, while true target, which is expressed by cancer cell, is separated at least by vasculature walls and a number of other physiological barriers. So in this situation, it's feasible that the radio-labeled antibody would be just intercepted by shed antigen. And this has been demonstrated in 2 studies using antibody amatuximab labeled with copper 64 or more long-lived positron emitter, zirconium 87. In this case, when too small amount of antibody, just 2 microgram, has been injected, activity in blood was pretty low, activity in tumor was not very high, but it was a lot of activity in the liver. And activity in the liver indicates that this antibody met methicillin in circulation, and this immunocomplex was dragged into liver. If you increase the amount of antibody, so with the same activity, so the cold antibody would relatively rapidly block everything which is in circulation, and the antibody would have its chance to find a tumor and target it and make an image, which has been demonstrated. So in this case, the imaging of shed antigen was possible just because injected mass of an antibody was increased and specific or molar activity was decreased. So conclusion is that increase of injected antibody mass permits to suppress an interception of labeled antibodies by shed antigen in circulation. And in this case, the optimal injected mass would not be the lowest one. So specific activity or molar activity, optimal does not mean the highest possible. There might be also more complicated cases, and that includes uptake in normal organ which express a target. Unfortunately, we very seldom have a situation when the target is expressed solely by cancer. Typically, it's expressed to a certain amount in normal tissues, but also in much higher amount in the tumor. One of the most difficult organs expressing normal tissues is the liver. And the reason is that first, liver has very well fenestrated vasculature. There is essentially no barrier between hepatocyte in the liver and blood. So they are in direct contact. And liver also is well perfused. Between 20 and 30% of blood volume goes through the liver during every turn of the circulation. And if the target is expressed on hepatocyte, you might be in trouble. This image has been produced by Chaitanya Divgi in early 90s when he tried to use anti-epidermal growth factor receptor antibody for imaging of lung cancer. This was before FDG, so antibody has been considered as a possible imaging probes for staging. So when he injected 4 milligrams of radio-labeled anti-EGFR antibody, it was just stuck to liver. So nothing essentially went into circulation. So there is not very high, but appreciable expression of epidermal growth factor receptor in the liver, which just sequestered antibody from the circulation. So what Chaitanya started to do, he started to escalate the dose. He injected the same activity, but he added more and more cold antibody. When he had 120 at the same time point, you could see what happens. So it's, of course, activity in liver is high, but antibody managed to break through the liver and distribute throughout the circulation, and in the end had a chance to find cancer and bind to it. And what he concluded that you need to inject at least 20 milligram of this antibody 2 to 5 to perform an imaging, and you need to inject 120 milligram to have an optimal image. One could see that here in this graph that with increase of injected amount of antibody from 40 to 300 milligram uptake in liver is decreasing, and the uptake in tumor is increasing. So some activity could be observed with 40 milligram optimal imaging at 120, and if you increase further to 300.
Ну, в сравнении с теми, которые мы потом смотрели, она там не такая. Мы какие мы больше смотрели. Не, ну, или Куба, там, помнишь?
Okay. Some artifact, sorry. So we need to have a certain mass of antibody to prevent uptake in the liver in case of imaging of epidermal growth factor receptor expression. Similar effect has been observed by imaging of PSMA, prostate-specific membrane antigen. Now it is a very famous target for imaging of and therapy of prostate cancer. Nowadays, John Babbage and Uwe Haberkorn have developed a short D-peptide which binds to prostate-specific membrane antigen with high affinity. However, the first attempt to image and to treat has been performed using an anti-PSMA antibody J591, and it has been shown that if you inject again too little, a lot of activity will be taken up by liver and very little go to tumor. If you increase tenfold, you could see that relative uptake in liver would be decreased, while a relative uptake in tumor will be increased. So, as a study by Morris and co-authors concluded that the higher antibody mass scans show the increased number of lesions. So sensitivity is increased when you're injecting more substance. Again, decrease of specific activity by increasing the injected mass resulted in improvement of imaging. Another target, very well known, is human epidermal growth factor type 2, and it's a molecular target in breast and gastroesophageal cancer. And if you inject too little, for example, 10 milligram, so it will be taken up by liver, processed, and in this particular case, 3 days after injection, all activity was in gastrointestinal tract, where it was excreted from hepatocytes. However, if you inject 5 times more, there will be uptake in liver, but activity will be distributed throughout the body, and there would be a chance to target and image the cancer cells. The same effect would take place when the imaging was performed at the same time with treatment with a coltrastuzumab. Again, activity was distributed throughout the body, and a number of metastases has been visualized 5 days after injection. Well, it's full-length IgG, so the contrast was not extremely high. We have observed the same effect when we used our antibody molecules for imaging of epidermal growth factor receptor. So one could see that if we inject 5 microgram per animal, the uptake in liver will be very high and exceed uptake in tumor. If we add 50 microgram of the same antibody and inject into mice, we managed to suppress noticeably uptake in liver without decreasing too much uptake in a tumor, which resulted in very noticeable increase of tumor to non-tumor ratio, imaging contrast, and made imaging possible. Oops. No, I think I have problem with program. I have to restart. Sorry.